Hi everyone. In this recorded lecture, I'm going to introduce the content of part 2 of chapter 1, Introduction to Mechanical Engineering Design. This is for the course of MCAE 420, Machine Design. And in this lecture here, I'm going to cover the concept of reliability and probability of failure and how to relate the design factor for machine elements to the concept of reliability. So let's start with definitions first. So what is reliability? So reliability is defined as the statistical measure of the probability that a mechanical element will not fail in use. And for the reliability, we will always refer to it using the symbol R for our calculations. On the other hand, probability of failure, we will always refer to this quantity as P sub F, is defined as the number of instances of failures per total number of possible instances. So the relation between the reliability and probability of failure is given by this equation 1,5, in which the probability of failure is equals to 1 minus R, or the reliability is equals to 1 minus the probability of failure. So the factor 1 is because both the reliability and the probability of failure are statistical quantities, that they have a maximum value of 1. They vary from 0 to 1. So that's why this relation given by equation 1,5 can be used. So for example, if we have 1,000 parts, mechanical parts to be manufactured, and then we expect that 6 of them will fail in use, then the probability of failure for this case can be calculated as 6 failed parts divided by 1,000 parts, the total batch manufacture, which is going to be equals 0.006 or 0.6%. That's the probability of failure. On the other hand, we can also calculate the reliability by taking 1 minus the probability of failure, which is going to be equals 0.994 or 99.4%. So it's more common to define the probability of failure and the reliability in percentage terms and understand them as a probabilistic number. Once we are able to define the reliability at the component level, so we can go ahead and find a way to calculate the overall reliability of a system composed by different components. Okay, if you think about any different type of machine which is composed of several different machine components that you put them together in a certain way, then we can calculate the overall probability of failure or the overall reliability of the system, assuming that the system is going to fail if one of those components fails. Okay, so we can do this by calculating the overall reliability of a series system as the product of the reliability of the individual components that form that system. The equation used to do this calculation is given by equation 1,6, in which R, the overall reliability, is the productory of all individual reliabilities. It doesn't matter how many components the system is going to have. So one example. So if we have a shaft with 2 bearings to support that shaft, and let's say that we can define the reliabilities of the 2 bearings as bearing 1 having reliability of 95% and bearing 2 98%. Then the overall reliability for the bearing system is going to be R equals to 0.95% or 0.95 multiplied by 0.98, which is going to be 0.93 or 93% overall probability or overall reliability for the whole system. Now that we have properly defined reliability, let's see how it can be used for the calculation of the design factor. So if you remember from part 1, we did some calculations of the design factor considering both the upper and lower limits of stress applied to the part and the strength of the material of the mechanical component. So if we're able to plot those charts here for both the stress and the strength, which are called the probability density functions, so we can determine directly the probability of occurrence of any value of stress and strength within their respective uncertain intervals. So what does the deterministic approach does? So the deterministic approach to calculate the design factor assures that those two limits, the upper limit of the stress and the lower limit of the strength, they stay far apart from each other, because that's what ensures safe design. So this approach assumes that any stress and strength values within their respective intervals have equal likelihood or equal probability to occur. But in real life, we know that within their respective uncertain intervals, some values of stress and strength are more likely to occur than others. So that's why usually, instead of having a flat probability density function, we're going to have this bell-shaped curve. And we are familiar with this bell-shaped curve because of our statistics classes. Okay, so the bell-shaped curve is the Gaussian function used to model the probability density function of any random variable, in this case the stress and the strength, and we need two parameters to fully define mathematically those probability density functions. The first one is the mean stress, which is the central tendency for both the stress and the strength, and we need the standard deviation, which is a measure of scattering, how scattered is going to be the bell curve around the mean. So the normal or Gaussian function is often used to model the probability distribution functions within uncertainty intervals. If you're going to use the Gaussian or the normal distribution function to model uncertainties for any random variable, in this case for the stress applied to a mechanical component or the strength of that mechanical component, then we need to define the equation that defines that bell-shaped curve, which is given by equation 1.7. So if we integrate this equation, we are going to be able to calculate the probability of occurrence of any stress or strength value within and outside the uncertain interval. As you can see, the integration of this equation is going to be very difficult if we're going to do it by hand, and we're not going to do it. So, but fortunately, we have some calculation tools or calculators that we can use to do this work, integration work for us. The one that I particularly would recommend to you all is the function in Microsoft Excel, which is called the norm.dist. So it's very easy to use with this function. We just need to define a couple of parameters in order to calculate the probability of occurrence of events for parameters that we can describe using the normal Gaussian distribution. So let's say that we want to use the norm.dist function to calculate the probability that a certain random variable x is below a lower limit x sub LL. So this is equivalent to calculating the area under the Gaussian curve for this red area indicated here in the figure. Okay, that's the same as calculating the probability that any value of x is going to be below the lower limit value. So in order to do so, we need to apply this statement of the norm.dist function. So the probability value, or the probability that we want to calculate here, is going to be given by the function. And that's what you can directly copy, at least the statement of the function. We can copy and paste in one cell in Excel. And then we need to address those arguments here. So XLL is the value of the lower limit, okay? So if you think of this X being the strength, so in this case here for XLL is going to be the lower limit of the strength. Mean, we need the mean value of the random variable of X, the standard deviation of X, and then the last argument of the function is going to be true. And this true here is because I want specifically to refer or Excel to give me or to return to me the value for the cumulative distribution function. So that's why I need to make sure that we're going to have true here. So another example is if we want to calculate the probability that x is above the upper limit xul. So we got to do something very similar. The only difference here is that we are going to calculate the area under the curve for this value here, xul and above. So that's why we're going to get this the probability or the area under the curve for this red section here. And then we need to write use the norm this function this way according to equation 1.9. So it's going to be given by 1 minus the whatever value given by the norm this function, in which the arguments are going to be the upper limit value, the mean value for the random variable, the standard deviation, and the true statement. Another example is if I want to calculate the probability that x is either below a lower limit value and above the upper limit value. Okay, in other words, this is the same as calculating the probability that the random variable is going to fall outside of the uncertainty intervals. So in order to do so, I need to apply this statement of the norm dist function, which is given by 1 minus the norm dist applied to the upper limit, okay, considering the mean and the standard deviation and the argument true, plus the norm dist applied for the lower limit, which is obviously given by the lower limit, mean, standard deviation, and the argument true. Let's apply the previous concepts through one example. So let's say that in a shipment of 250 connecting rods, the mean tensile strength of the batch was found to be 45 kpsi and the standard deviation 5 kpsi. So for question A, assuming a normal distribution, how many connecting rods can be expected to have a strength less than 39.5 kpsi? Question B, how many connecting rods are expected to have strength between 39.5 and 59.5 kpsi? So this is a problem in which from the batch of identical connecting rods, so we are able to apply some statistics to measure the strength, the tensile strength of all individual, each one of the connecting rods, and then we calculated the average or the mean and the standard deviation. And then we are interested in applying the statistics through the norm dist function for the limit between 39.5 and 59.5. So to answer part A, so we have to consider the lower limit, 39.5 kpsi, and then we need to apply equation 8 or the statement of the norm dist function according to the one given by equation 1.8. So if we want to see to the look at the graphical interpretation, so this is the same as calculating the area under the Gaussian normal distribution curve between minus infinite and the lower limit right here. So I did everything directly in Excel. Okay, so I made sure that I would put each one of the parameters of the norm-dist function in one of the cells in column B. So you can see here that the lower limit value 39.5 is in cell B1. For cell B2, I have the mean value. For cell B3, I have the standard deviation. And in cell B4, I did the calculation of the probability I'm looking for. Okay, so the result here is 0.135666. Or if I want to use the percentage notation, I'm gonna get the result as 13.57%. So these results mean that there is a probability that, or at least 13 point is expected to have 13.5 or 13.6% of the connecting rods of the batch with tensile strength less than 39.5 kpsi. So in order to find the exact number, so all we need to do is to multiply this probability number we just calculated here by the total number of connecting rods in the batch. So if I multiply one number by the other, I'm going to find that approximately 34 rods will have tensile strength less than 39.5 kpsi. For part B, we are pretty much interested on calculating the probability that any value of the tensile strength is going to fall within the intervals, 39.5 and 59.5. One thing that we can do is, since for part A, we've already calculated the probability that the values will be below the lower limit, we can go ahead and calculate the probability that the values will be above the upper limit, as represented here in this graph here. We're going to add the two probabilities, right? Such that we're going to be calculating the probability that the tensile strength is going to be outside of the interval. And then we subtract that sum from 1 to calculate the probability that the tensile strength is going to fall inside the limit intervals, which is exactly what part B is asking us. So let's go ahead and calculate this probability using the upper limit. Then I have here the Excel statement. So I'm going to be using the statement given in equation as in equation 19, which is given by 1 minus the norm-dist function for those arguments here. Keep in mind that since I'm using the upper limit here, so I have the upper limit for the tensile strength, I have the mean value, and I have the standard deviation. So in this cell here, I have the result, which in percentage terms is going to be 0.19%. So next, what we're going to do, we're going to sum those two probabilities we just calculated. The probability 0.19% and the probability that we've calculated in the previous item, which was 0.1357. And then we're going to subtract that sum from 1 in order to calculate the probability that the tensile strength is going to fall within the uncertainty interval, right? So I'm just putting this statement here. I've already calculated the two probabilities, and then I'll just do the math here, and then I'm going to get that I expect that 86.3% of the rods will fall within the interval given by in the problem statement. Okay, so in order to calculate directly the number of connecting rods, I need to multiply 250 by the probability I just calculated here, 0.8625, which is going to give me approximately 216 rods. this point, it's very clear to us the differences between the deterministic and the probabilistic approaches to calculate the design factor. Whereas the deterministic approach only considers the information, only takes into consideration the information of the limits of the uncertain intervals for both the stress and the strength. The probabilistic approach or the reliability analysis considers more information regarding the shape of the normal Gaussian curve. So that's why probabilistic approach are usually more accurate as long as we have good statistical data available to estimate the statistical parameters of both the stress and the strength. So once we are able to do this, we are able to come up with the Gaussian normal distribution curves for both the stress and the strength. And then we can play with how much we want them to be close to each other. Because depending on how much they overlap, the shaded area below the overlapping of the two curves is going to give me the probability of failure of the mechanical part. Overlapping area under the PDFs of the stress and strength is a parameter that we can control in reliability analysis. And how are we going to control it? We're going to control it through by defining a reliability goal in order to guarantee a safe design. So we're going to do this through this equation. We can define this reliability goal or our goal by taking the risk acceptable for the design in terms of how many fails we can accept for the design and subtracting it from 1. So let me give you one example. So let's say that we are going to manufacture a batch of 1,000 connecting rods, identical connecting rods, for which we accept that only one of them will fail in service. Then the risk in this case here is going to be 1 over 1,000, which is going to be 0.001. And then we can calculate the reliability goal, our goal, which is going to be 0.999. This value is going to be very important for the calculation of the design factor using the probabilistic approach. Okay, and this is the same as defining the target reliability as well, which is calculated in terms of the target probability of failure. Those two equations, they represent the same thing. So we can calculate that. So we can calculate the average design factor, considering that for a probabilistic approach, the design factor is also a random variable. There is uncertainty on the design factor, and then we can use equation 111 to estimate the design factor using reliability analysis. So let's go over this equation to understand each one of the terms. So what I need in order to use this equation, I need to have the statistical information about both the applied stress and the strength. And they are given by this parameter C, which is the coefficient of variation. We have CS, which is the coefficient of variation for the strength, which is nothing but the standard deviation of the strength divided by the mean of the strength. We have C sigma, which is the coefficient of variation for stress, which is the standard deviation for the stress divided by the mean stress. And we have the plus minus sign here. The plus minus sign here is just a sign that we're going to pick depending on the value of our goal, of the target reliability. If we are going to design for a target reliability which is greater than 0.5 or greater than 50%, then we have to take the plus sign. On the other hand, we're going to take the negative sign if the target reliability is less or equal to equals 0.5. And the parameter Z in equation 111 is called the inverse of the standard normal cumulative distribution function, evaluated at our goal. So fortunately, we can also calculate this parameter using Microsoft Excel. Then we're going to use the function norm as inv. And then the parameter to be used on that is our target reliability, or the reliability, the goal reliability. So this R goal usually is given, and it's given, as I mentioned in the previous slide, based on the amount of risk we are going to take in order to accomplish the design task. Now let's see one example to demonstrate the application of those concepts. In this example, we have a round cold drawn 1018 steel rod that has a mean yield strength of 78.4 kpsi with a standard deviation of 5.90 kpsi. The rod is to be subjected to a mean stress of 50 kpsi with a standard deviation of 4.1 kpsi. Assuming the strength and the load have normal distribution, what value of design factor corresponds to a target reliability of 0.999 against yielding? Also, we need to calculate the allowable mean stress for this condition. So first, it's clear that we're going to use equation 111 given by the reliability analysis to calculate the design factor. So first, we need to calculate the coefficient of variations. We have two to calculate, one for the strength and one for the stress. So let's start with the strength. So for the coefficient of variation of the strength, we need the standard deviation, which is given the problem statement, 5.90, and the average or the mean for the strength, which is 78.4. Then by doing the math, we're going to get that CES is going to be 0.0753 for the strength. Repeating the calculation for the stress, we're going to calculate the coefficient of variation for the stress by taking the standard deviation for the stress, dividing it by the average or the mean for the stress. Then the result is going to be 0.082. Then the next parameter we need to calculate is the parameter z. Remember, the parameter z given by equation 112, we need to use the normal inverse cumulative distribution. Then we're going to apply that function as stated here in equation 112, and applying the parameter, which is given by our target reliability. Then we're going to get the result as 3.09. After that, we're going to finally substitute everything into equation 111, which is going to read like this. Keep in mind that we have to take the plus sign, since the target reliability here is 0.999, which is greater than 0.5. So that's why we need to use here, plug the plus sign. Then plugging all the values, the two coefficients of variation, the z value, we do the math, and then in the end, we're going to get that the reliability design factor, or the design factor calculated from the reliability analysis, is going to be 1.416. In order to answer the second part, the second question, we need to use equation 13 that you can check back on the slides for part 1. That gives us how to calculate the mean stress if we have the design factor and the strength of the material. So in this case here, since we are using reliability analysis, obviously we're going to be calculating the mean stress based on the mean strength and the mean design factor we just calculated. So plugging all the numbers, we're going to get that the mean allowable stress for this condition is 55.4 kpsi. So these results indicate that the rod supports up to 55.4 kpsi as the mean stress. Remember that this is a statistical quantity. If we want to maintain this reliability of 99.9%. So all results we're going to get with this analysis, it must be obtained from the definition of the target reliability or the risk that we're going to accept for the design.